Awesome. Greetings, healthcare colleagues. My name is Kevin Kawchak. I'm the founder, CEO of Chemical Q Device, here for discussion 87. This is June 15th, 2023. And this is mostly going to be about how to code with quantum machine learning in healthcare. So, as you may know, quantum is a real thing, especially on quantum simulators these days. And in specific, with QML coding techniques, they'll be discussed. And with input medical data, such as omics, so this is genomics, clinical notes, longitudinal data, demographics. Actually, 90% of all healthcare data is imaging data. And then I'll be discussing some QML platforms and libraries, and this is open for discussion as well. Specific aspects of quantum algorithms, so embedding layers, you have variational quantum circuits, you have basically measuring or condensing the qubit into a 0 or 1, and scaling to classical code. So as you've heard me talk before, it's not going to be just the algorithms. You have to take into the account complexity of both classical and the quantum, methods being combined. Are you overfitting? Do you have to do other things like dropout? That's common with convolutional neural nets or even transformers too. So it's going to be more about applications, I think, than any specific algorithm moving forward. It's just there's a lot going on between if you have thousands of medical images or other types of data. It's the combination of quantum and classical, right? It's not going to be just insert a quantum algorithm and then it fixes everything. It's more like you have to consider multiple things. So I wanted to open this up. I know some of you definitely have a machine learning background and even a medical background as well. So from that point of view, I guess what's the main thing? Any questions or comments as far as moving forward? And I have notes here and I can go through as well. But I get that feeling like, people really want to code in quantum. They just don't quite know how to. They don't know quite where to start. Those types of things. So feel free to unmute and you can come on as well. So I saw Ron or Edwin. You're free to ask any questions or kind of comment of where you are with all of this in quantum. And it's definitely exciting, right? So you have medical data concerns of not having enough medical data. You have some issues with classical neural networks that could potentially use the help of quantum as well. And I guess kind of like pinpointing how exactly is this quantum gate going to make the model run faster, which I've made quantum circuits made run faster, get better performance likewise off of specific models. And how does that apply to your application in inserting quantum with this? And then I also saw Zoran or Kevin, you're free to unmute and then you can come on as well, ask any questions you want. So definitely, if you haven't gotten started with this, I would definitely start with gates and circuits. And then, so I think Ron put something in the comments here. Yes. So how to code in quantum machine learning. So if you're currently working on any, specific application in medical that you would want to add quantum to.
I think do you hear me, Kevin?
Yeah.
So I think that depends on what level you are coding at. You can code at the circuit level. You can code much higher. For example, when we did our work that we published a year ago, that was a hybrid pipeline, which is often the case. I think it's practically a classical machine learning pipeline, but we took a SVM model, the support vector machine model, and replaced it with QSVM, which is the quantum SVM, because that's one of the models that exists in quantum space. Like XGBoost doesn't, as far as I know, for example, because it's different, but this one is linear algebra based, and so that has the quantum parallel. So you effectively have the pipeline which exists in classical, but you take one component and then do it two ways, classically and quantum, and that kernel then that you get participates in your pipeline just like you calculated classically. You just know this is classical, this is quantum. You compare the results. Effectively, it's the part where you find one thing that could be taken into quantum and the rest is as it is. And so that way you can make comparisons. Is it speed? Is it accuracy? That depends on what you're looking for. For example, with Monte Carlo in quantum, maybe you get speed. I don't know. I haven't tried that, but this was just, that's just one way to do it, I think.
Yeah, I really like that paper. In specific, you talked about, and this is with the Dr. Frederick as well. You talked about the explainable AI, how you could potentially, and I think you guys made an effort with that. I like that paper because it's so much different than a lot of the other, let's say I have like 6 or 7 other medical image analysis papers.
Mhm.
And it's definitely unique that I had to reread it twice. And I actually reviewed it once. I think on LinkedIn there. And then
Oh,
was there anything else you found? I think you used the IBM real hardware for part of it,
right.
correct?
Yeah, we had a contract, IBM and Amgen had contract, and so this was done as part of that collaboration. And we had access to 27 qubit IBM Q underscore Dublin was the instance at the time. And we had it in dedicated mode for about 6 weeks. So we blasted it just full time, basically running.
Yeah, that's very cool. So I would encourage everybody to check out this paper. I forget the name of the title, but it was with, I believe, three researchers with it. At least you and Dr. Frederick used to work for IBM.
Frederick Shahab, who is also Omar Shahab from IBM Quantum team, and then Nate, he's also part of IBM Quantum team, more on the backend hardware side, and another data scientist, George Segan from Amgen. So, but the title is Quantum Kernels for Electronic Health Records. Effective. If you Google that, you'll find it.
Yeah, it's an IEEE paper. I would recommend it to a lot of people just because of the thoroughness of it. And then you can learn a lot as far as, okay, you're running on this hardware, it has these restrictions. What can you do moving forward with that? So that was one of my favorite papers for a while,
Thank you.
just one of my introductory papers, I would say.
Thank you. Thank you, Kevin.
Yeah.
Hey, I'm currently a provider of medical software for private practices that incorporates a medical record subsystem. So for I'll probably not pronounce this right. Zoran.
Zoran, yeah, that's
Zoran.
correct.
I'll just call you Zoran. Oh, that's.
Yep.
I have some Serbian friends with that name. Can you just give a brief statement of what you did regarding medical records and the use of quantum?
So we used, when we started this, there was a project that preceded this one where I had a chance to lead it at Amgen. So that one was electronic health records, and specifically something that Amgen uses. It's coming from United Health Group from Optum, which is the big technology division, and they sell electronic health record data set. And so we have that, we license that. And so we had a project where we did predictions for patient outcome, specifically for rheumatoid arthritis patients, where we were predicting their persistence, meaning if patient starts a medication for rheumatoid arthritis, would they stay on it for 6, 9, 12 months, for example? Because usually the patients that started, they stay on it for the rest of their lives. It's relatively rare that they go into remission. So usual expectation is if they start, they would stay on it. So if they don't, companies and health insurance and medical community likes to know why, doctors, clinicians. So that's the prediction. It's a binary classification, yes or no. You take 1 year of data. That's what we did. In front of what they call index date, which is when you start taking, as a patient, start taking medication, take year of data prior to that, and you can structure it for any kind of deep learning model, SVM, whatever you want, and then XGBoost, and then you make a prediction using the prescription patterns. You look at the prescriptions 6 months out, and you say, okay, after 6 months, does it look like this patient is still using these prescriptions or not? And it's slightly different between persistence and which is really based on prescriptions versus adherence, which is when patients actually do really know if they're taking medication. They could be going to pharmacy and getting prescription, but they may not be taking medication. That's different, but this is just based on prescriptions. And so once you have that, that's your binary classification. And we used to do XGBoost, SVM, some deep learning models. When we did quantum, then we did QSVM because it exists in quantum space. And so that was the simple logic, because you don't really have a choice. Like, and I think Kevin talked about it before, but you don't really program the quantum computer conventionally, right? So you want something which people in quantum research had already, quote unquote, ported over to quantum, right? And so there are some neural networks that have that, and SVM is one of those that's actually commonly used, I think, in finance for future predictions and things like that, but we chose to do it because it was available. And so that transition was not too difficult, although it took us a little bit of time to just wrap our head around the whole thing. But so that's really the kind of the short version. Paper has lots of details, but that's not kind of the core of it.
Okay, so you accessed an anonymized database of patient medical records, and I mean they probably had identity information stripped.
Yeah,
And,
so when you buy the commercial electronic health records, it's de-identified, so that's absolutely a legal requirement, which is why you, for example, see we used to have a version where there was a, I think, income range and education of the person was provided, and then they took that out to give you something else. So they only have so much information content they can provide about the person. Or, for example, you see that, and this is not really a quantum question, but there is no patient older than 90 or 85. That's actually a FDA HIPAA requirement because those are rarer, and so the patients that are so rare will be easier to identify. So everybody who is 92 becomes 90, for example, right? So that way they try to have that bucket to be big enough to prevent somebody from identifying patients. So you have some problem. I think that's less of an issue because the age range, for example, and those kind of things are good enough. I think problem is you don't get a region, or you got only the region, you don't get the zip code, for example, for somebody. So that prevents you from doing anything that's localized, or you may not have some other parameters that may be helpful. I think we were particularly interested in zip code information because there is lots of clinical trial work that happens, and it's related to the zip code, the hospitals that are available, a lot of other things, but it's a commercially available de-identified data set, and so that's not the only one. There are others, but it is. I think the bigger problem you see is the noise in medical data that comes from a variety of medical systems across the country, because Optum EHR data set covers 104 million patients in US as of a year and a half ago. So now it's probably even more. And so that's 40% of the insurance population in US, I think, almost, that has insurance. And so it is large, but the quality of the data is, up and down depending on which part of the data. Lab measurements are better. Prescription patterns are problematic for a variety of reasons, but it's a longer discussion. But it's interesting to look through and see, what kind of patterns you can find there. It's definitely
So, and then you initially set up with classical machine learning to do some predictions?
Yeah, we do that routinely for a variety of other, I did predictions for different diseases. That was one of them. But then when we started quantum, because I knew this one and I had a couple of years of experience working with clinicians, rheumatology specialists that were on my project. So you kind of understand the clinical setting. And that's really helpful when you interpret the data and try to do anything, so that when you understand what's going on in the data, for example, why prescriptions are missing sometimes. You have to make some heuristics around predicting that 6 months persistence, is it yes or no? It's not a clean cut. But that helps. And so then going to quantum was basically you're just swapping one component of the project for another. It's almost like mathematical model is swapped with whatever it takes to learn Qiskit, for example, which depending on what time you have available, maybe.
I see Kevin posted the link to your paper, so I'll just ask you like 2 more questions. So you were able, after you had your model built, you were able to do predictions like or make some predictions like on drug efficacy, and specifically not like
This one
chronic
is for
drugs,
persistence. So will the patient stay on medication or not? That's the persistence. That's the binary classification.
Okay, and then when you switched over to quantum, you said it was the quantum support vector machine.
QSVM, Qiskit supports it. And if you dig in through the Qiskit documentation, there are a couple of ways to do that. And-
So just briefly, where did you inject the quantum SVN at the beginning of the machine learning stack, or did you attempt to replace a layer, or just
So the whole
just
QSVM is basically you're taking. So if you go to Python code, for example, and you look at the scikit-learn pipeline, right, which you can structure it manually or use the automated way. There is a place where you have what's called .svc model. So the function is literally .svc, right? That's for support vector option. And that's the one where you provide your training data set and your test data set. And then there is a way that they calculate the matrix products. And so it flows from there and you get that back. And then you make predict probability. And then from that prediction, you get false positives, false negatives relative to your true labels that you know in the test data set. And then you can construct the confusion matrix and all the metrics, all the measurements that you want to do, let's say accuracy, balance accuracy, Brier score, whatever you want, depending on the context and depending on what your users think are important metrics for them, sensitivity, specificity, and all of that. So really the only thing that changes is then when you instead of running the SVC, you're running the QSVM, and that goes against the quantum backend. And then,
okay.
you will take longer because SVC for small data sets of couple of hundred records will run literally instantaneously, practically. The quantum one will take, back then was taking hours. Now it's faster, but it still takes a long time.
Very cool. So I know we have some new people coming on here, and we've talked a little bit about, that transition from ML to QML, which parameters should I change in QML? Am I using Penny Lane? Am I using Qiskit? I know Emin has been on before. Carlos has been on before. Are there any questions concerning that as far as it's not just a drop in. I'm sure, Zoran would say the same thing. You can't just insert a quantum circuit here and expect the performance to be better without changing the complexity. And that we're talking about overfitting or even benign overfitting, those types of things. So is anybody kind of stuck on a QML project that they've been working on? Zoran's, I believe, was rheumatoid arthritis, the paper that I put in the chat there. And one of the first, big papers that got me really excited about the field in medical and quantum. And, so anybody that we haven't heard from, so Alina or Gil, any questions regarding, quantum circuits, quantum gates, quantum machine learning, how it all fits into a conventional classical model? And I would say Zoran kind of touched on the scikit-learn stuff, as a lot of it's hybrid, right? So you're going to have a portion that is now quantum code that was classical.
I'm still just listening. I've done a lot with classical machine learning, and so it's just seeing how they connect. So I may have some questions at the end.
Yeah. I mean, that's a good question right there, because the key is if you haven't gotten into quantum, is that you have to have some way of relating it to classical. So at the end part, you measure and it collapses it into a 0 or a 1. And then you can take that, that bit information and work with it classically. So during the rest of the, the first and the middle of the circuit is basically you're encoding into quantum data and doing some stuff with quantum. And then it goes back into classical at this stage with, linear quantum circuits where we're at right now.
Yeah, Kevin, hi, this is Alina. I'm so ignorant in the field that I am in the wrong meeting. So I was trying to learn something, but I know nothing about this, so I can't ask questions at this point.
Well, that question could go a number of ways, but I'll answer it in this way. So quantum mechanics or quantum computing allows you to do entanglement, superpositioning, interference. You can have greater feature spaces, just like you can do classical, but it's tied to interference. So that's what's having great promise for image classification, is you're spreading out images just due to the inherent nature of a quantum bit. You'll mostly hear it in terms of entanglement, but for many of the applications I've had, I'm not necessarily taking care of entangling.
No.
You have some, Ron? So
sorry.
it just depends on the application, right? So it's just if you're trying to do and you can watch a bunch of penny link videos, it's a big one, and read the papers too. They'll say sometimes the circuit you don't need for this application, the part of it. And in other ones, if you're doing, hundreds or thousands of qubits, which we don't typically do, is that more entangling gates, but it just depends. So if you have an application that you're working on, definitely, feel free to share it. I shared some of the data, omics, genomics, and clinical notes, longitudinal data like Apple iPhones. I don't think they've converted over to, quantum simulators and hardware yet, but collecting data over time. So how can quantum help with that? Demographics, drug discovery. There's at least 10 organizations working on drug discovery. So this is Johnson Johnson, Benton AI, Polaris QB. So it's just approximated, right? It's not full quantum effect at this stage.
I did have a question.
Yeah.
So, one of the areas that my group is doing research in is in material science and discovery. So what I want to be able to do on the machine learning side is actually, as you said, integrate the quantum portion of it into what we do the deep learning now. But actually, because it is an optimization problem, it seems that there's a lot of promise in using quantum learning in this area. And so I don't know if you have any experience in that with material science, and those are large databases of materials, lots and lots of samples, but there might be a better way to express the features within the sets in the quantum realm.
Yeah, I mean, what's mostly being used for that is a technology called quantum annealing. It's mostly done by D-Wave Corporation and Fujitsu. Most of the drug discovery stuff, because you can get up to 5,000 qubits, and it's just for optimizing things. So typically, you could, look at D-Wave's website. It's got 250 plus applications so far. It's just it's going to have some noise, but I think the end result, as long as, well, I don't know how crucial or life, like for medical, it's going to have some noise because it is real quantum hardware. It's just not like the full out thing. It's called quantum annealing. So I would definitely check out D-Wave. They do stuff. Okay. Feature extraction. That was just within the past, I think, 3 months that they said, yeah, by the way, you could use our tech because of the elevated qubits to do, feature extraction a little bit better than some other, especially the other hardware manufacturers. So they're kind of, I wouldn't say they're the dark horse, but they've been around for over 20 years. It's just the tech, it's for specific problems. Like in theory, the rest of quantum might catch up to it. That's the thought, right? If there's another breakthrough, but it's good to get started, I would say.
Okay, would you mind putting that in the chat? Link to the.
Yeah, it's just D-Wave for that.
Okay.
So
okay, great.
And I'm connected with a lot of the people on LinkedIn. So I would definitely check out annealing. And then you're going to find some cool stuff with simulators, because NVIDIA already has GPU quantum simulators, multi-GPU quantum simulators. They've already simulated over 1,000 qubits using tensor network quantum circuits. And there's no noise, right? So you don't have the noise with quantum hardware, but it's going to be slow. Maybe 6x, I'm getting like 7x slow. But they said if you use multiple GPUs, you can start to get it inch the time back down to classical running time, but it's not apples to apples, right? The classical hardware is always going to just run faster than a GPU simulator, but that's the direction where I'm kind of going. I definitely want to get up and running on a single GPU. They're more practical probably to pitch, like for a business, say, okay, I use a single GPU quantum simulator to get the qubits up for this specific type, and then the runtime down from a CPU quantum simulator. And, keep reading the news. I mean, just as a whole, IBM, Intel within this week, they both had big announcements for their quantum hardware. Again, the noise levels, if you're talking about thousands of images in a machine learning workload, you're not talking in that same area. So you're talking like, a lot smaller models still for a lot of the quantum hardware, like for, practical applications.
Intel announced a 12 cubic silicon chip this morning.
Yeah, this morning, yeah.
Yep.
It feels like yesterday, but yeah.
Well, I saw it this morning, to be more precise. I'm not sure. Maybe it was yesterday. Yeah.
Yeah. Yeah, so it's 12 qubits. I scrolled to the bottom, they said 95%. So of course, with classical computing, we're 99 point many nines. With many quantum hardware, it's 99.99 for like
Yeah.
a two qubit gate fidelity.
Yeah.
So anyways, it's all good news, right? Because it keeps getting developed. I guess the thing, and Jordan can talk about this too, is that it's made off of existing semiconductor lines, unlike the other quantum hardware. So silicon spin.
Room temperature. So yeah.
Yeah. Oh, is it room temperature?
I'm guessing it didn't say anything about cryonics. So I think that's a pretty big deal. If it's cryonics, then that's gonna kind of.
Yeah. The last I heard was it's 1 Kelvin, and that's like 1,000 times warmer.
Oh, they still have to cool it. Okay.
Right.
Oh,
But it's
all
not
right.
like a millikelvin like IBM
Okay.
or Google in theory.
Right.
So.
Right. Oh, cool.
So anything with software, anybody working on any projects in software? So this could be you're passing medical data, machine learning, and you want to add quantum, or have you already added quantum to your hybrid model? So anybody we
Hello?
haven't heard from? So Kevin or Edwin? It could be just
Hello?
where you're at with all. Yeah, go ahead.
Oh, I'm a student of machine learning, and I'm only experimenting. I'm only like learning quantum computing. Yeah. So I think one of my curiosity while attending this talk is the applications in drug discovery chemistry. Will you please explain more about that?
Yeah, so again, these are approximated models. I mean, this is as of 6 months ago, but I haven't seen any other huge breakthroughs. So typically you would have like a protein and you would only look at a specific portion of it, and you wouldn't look at it in 3D. You would flatten it into 2D, and you would use something like the quantum annealing that I was talking about, the D-Wave stuff. And I've heard that they're getting somewhere with it all, because say your client wants something in specific, and you can do, based on these other approximations with annealing, something that has performance over classical, right? So that's called quantum advantage. And Johnson Johnson is partnering with with another company. I forget their name, but there's Metin AI, Polaris QB. So Shahar Keenan, so she's the CEO. She was on this discussion before, and that's basically it, right? Like you can do cool stuff with quantum annealing, but it's just for very limited things. So for drug discovery, I'm pretty sure they use simulators, right? So it's not going to be a real quantum computers for most things. I don't think, because of you have to keep the data kind of low for that. So yeah, it just depends on the application. And I've seen a Johnson Johnson pitch deck. I've seen Polaris QB. Shahar just talked, and I researched her organization. She just had some pretty big news. Like it sounded like a platform that they're coming out with. But I would say the two probably main things are quantum simulators and quantum annealing at this point, because it's a relatively big field for what quantum is. Like I said, over 10 organizations have launched efforts in drug discovery with quantum. And typically, this is quantum computing that I'm talking about.
Okay.
So yeah, it'll absolutely surprise you at the amount of research that's being done in this field. Anything from basic quantum computing, if I need things fixed, to quantum machine learning. Now, quantum machine learning, I just want to explain this a little bit. It's typically you have a linear quantum algorithm that's supporting some other classical neural network. So quantum machine learning these days is more like quantum linear algorithm plus the classical network that's doing most of the processing. But it can have an impact because it can change data in a certain way. So we don't have reliable quantum neural nets, or not like mainstream yet, but that would be the next step, is training data off of quantum neural networks as the qubits get up, especially over like 100 and probably a lot more than that. But yeah, that's kind of like the era that we're in, is this linear quantum circuits, I would say. Any other questions, Edwin? And then if not, anybody else we haven't heard from? I saw Carlos came on, and then Amin or Kevin.
Hi.
Yeah, go ahead.
Hi. When I attended the meeting, you talk about the quantum support vector machine. So I want to say something about quantum support vector machine. You know, in QSVM, we have a problem in the feature mapping part, because the mapping the features from the classical vector space to the quantum vector space, it means Hilbert space. Selecting the most suitable feature map is very important. You know, we have some feature maps, let's say Pauli feature map, Pauli X, Y, Z, and also ZZ feature map like this. So the selecting the most suitable feature map, it depends on your data set. I think it's my experience. And also in the quantum hardware part, I can say that, you know, we in the NISQ area in this part. So we have a limited qubit number in our circuit, and also we have a limited circuit. So it means that if we use more gate for our circuit, if you remember, last meeting I said that if you put the many gate in your circuit, it takes many time to processing. So it takes two hours, or let's say 3 hours when compared to the classical support vector machine, let's say. So these are very important in your circuit part. As for example, quantum support vector machine or any other quantum version of the machine learning part.
Yeah, I appreciate that. I'm about to go through, it's the Qiskit circuit library. They have a bunch of different circuits, and I think they pretty much split them up between entangled and non-entangled, and the entangled circuits will cost you time. So I would definitely investigate that. Like, do you need C0s here, or CZs, or, you know, CYs, those types of things? And, you know, they seem like they're more tried and true. So obviously it's out there. You can change the number of layers. What platform are you using?
Qiskit generally, and Circ also.
Yeah, so I would check for circuit library. So if you see things like real amplitudes, ZZ feature map, Z feature map, all of those are modifiable either by layers, or you could just switch to something else. So a Z or a ZZ are typically your embedding layers. Z does not have entangling, a ZZ does. And, you know, like, especially if you want a bigger ZZ, that's entangling plus more layers. But I would say that's what I came across, is basically those are your two main time things, if it's entangling or not. Because you don't always need entangling for certain things.
But also, you know, in the medical imaging part, we have, for example, in the MRI part, we have a noise in the images. So if you use these images, for example, also it affected the result of our.
Yeah, how many?
Totally, I have 75 images.
Yeah.
So
are you, if you're not using transfer learning, you'll probably have to bump up, if you can bump up. Because with transfer learning, it's already trained on ImageNet, 1,000 images, and then you're doing, you know, whatever, your convolutional neural net, and then you don't need as many. But yeah, I would say you probably need a lot more for your training set, and you can get a lot of images off of Kaggle for free. Like, I can get like 3,500 plus in like 44 classes for brain images. So yeah, that's probably the main thing, is you're probably going to have to get your training data set size up.
Yeah. So also, for example, I want to improve the MRI images when, you know, in the MRI images, there are many studies to improve or to reduce the noise in images. So for example, I want to use quantum CNN part for this platform. You know, we have also quantum transfer learning methods too. But on the Penelline support this quantum transfer learning part, but I know only this. Maybe the other platform also we can use. So the correlation between the medical images and also noise very affect the result. Yes, it's my opinion.
Okay, so just to make things clear, you don't want to change the images, correct? Like you just want to increase the images or do something so you don't get as much noise.
Yes, I
Oh.
don't want I don't want to add the new images in my study because these images come from the hospital. We have a collaboration with this hospital. You know, very limited images for transfer learning. For example, if 75 is the very small size for the using for the QCN or CNN part. But I want to improve or I want to reduce the noise in the images with using transfer learning or any other CNN part. This is my another study part.
Yeah, well, transfer learning or QTL, quantum transfer learning, it has a convolutional neural net. So you can do like a ResNet 18 or 34, all the way up to, I wouldn't recommend to like a 152. So typically the smallest one. And then they've done ants and bees on it with the image data set size that you have. So like less than 100 or barely over or 200 or something like that. I had 3,500. And you can get by because ImageNet is trained off all different types of edges of things that you find in nature and are man-made. And then you can take that, what you learn from that, and apply it to a relatively small training set and validation set too. So I would definitely check out that QTL, Penny Lane, ants and bees, and then you can adjust your classes. So I got 10 classes out of it. So it seems to be by far, and it allows any different size image. It says any image, color image, large image, small image, grayscale, doesn't matter. That's why I really like that model too, because it's set up so you don't have to manipulate images before using them, which is, it sounds like a trivial task, but it can be difficult. Anything else?
So, Amin, I understand you've written a paper on quantum support vector machines.
Yes, I have a paper about the quantum support vector machine. Nowadays, I study variation quantum classifier for medical images, medical applications. Yes.
Awesome. I hope you'll share that with us. And you were talking about noise in medical images. I have seen quantum image processing algorithms that are designed to remove noise. They do it by amplifying the bad pixels really hard. And then it requires a hybrid technique. So once you've processed the image with the quantum algorithm, that again, it amplifies the bad pixels. You use a classical technique it's called despeckling, I think, and use a classical technique to remove those pixels. Have you looked into anything like that for reducing noise in the images?
So you recommended to me hybrid system for noise in the future?
Yeah, this would be more like a pre-processing step where we'd be using a separate quantum algorithm to pre-process your images in an attempt to remove some noise from them. I don't know whether it would really be viable for MRIs or CAT scans or anything, but I have seen those type of algorithms float around, so might be of some interest, but I'm not sure.
Okay, thank you. I will look at the hybrid system. Maybe it can be useful for my application. Thank you.
Thank you.
Anybody we haven't heard from? So I think we heard from most people here, and I just want to comment. So basically, machine learning and especially deep learning is a thing in medical. The first deep learning FDA approved algorithm was 2017 by a company called Arteris. It's cardiovascular. And, you know, when you see these things, especially like Viz.ai, AI Doc, Huron, especially subtle medical, is they'll find an algorithm to basically, you only need one MRI scan because it can turn the noise into something that's like an image if you had 16 scans, so a reduction in number of scans. So those types of companies definitely are using, and especially in radiology, you know, the time sensitive thing, you know, you need to find out exactly what's going on in a patient. You do have to research a lot to see what's out there in medical, especially in deep learning. what's actually being used. But after that deep learning approval in 2017, there's a bunch in reconstruction, segmentation in medical for FDA. So that's definitely interesting. Any other questions or comments with this, either on the machine learning side or on the medical side? Gil or Carlos?
No more questions for me, but thank you.
Yeah. Yeah, and I would say a lot of this and the approvals is coming from cybersecurity now. So if you did not know, back in December 2022, there's a law now that requires all federal agencies to implement cyber quantum defense. And then, so there's a couple ISO, IEC regulatory things that just passed to the next thing. They're called approval. And then they've got some more stages after that, but that's news to me. And then, Sandbox AQ and Mount Sinai have a partnership with patient data and cybersecurity with quantum. So that's the pressing thing right now. I mean, medical will come, and we are talking patient data security here. But that's what most people are concerned about. If somebody has an awesome quantum computer overseas, how do we defend against it? So these algorithms are by NIST, and I think they're also implemented by NSA. But that's going to help push things through in my opinion, because that need for these quantum algorithms on simulators, and if they work well, which we think they will, start to see it to other fields such as finance and medical. I guess the other stuff is EHR data. So EHR data back in 2008 only accounted for 9% of all data. So it's electronic data basically. And in 2015, that's 84% is electronic medical records as opposed to, written data. So that's opened up the field enormously for machine learning, deep learning as well. And I mean, you have ICD-9 going into ICD-10, more codes, those types of things. So I think it's the biggest thing for me was going from classical non-machine learning, like a locked algorithm, as opposed to right now for, classical machine learning, deep learning to quantum machine learning, because it's basically running on CPUs or GPUs. But the actual people are buying into deep learning is the point. And there's a lot of resources on this. I've shot through, I don't know, 5 or 6 different MIT, their medical data and machine learning. And in order to understand QML or quantum machine learning, you have to understand the basis of machine learning. There's an extra processing step in quantum, but the whole framework behind it and Bayesian networks and how everything kind of developed in medical is based on classical. So I would definitely check those out. And there's so as far as getting data, and especially for Amin too, is there's places to get data and they're de-identified. I know I haven't checked it out yet, but MIT has this thing called MIMIC, M-I-M-I-C, and it's basically de-identified patient data. I believe it's public, and it's probably been updated as of 4 years ago. That's the key, right? Is more and more data, right? To get better results, more confident results, those types of things. Awesome. So Amin posted the paper in the chat, and then so Edwin said IBM meetup for quantum computing for creative and artistic purposes. That's good to see too. If it starts to spread to all aspects of society, it's best for finance, medical, transportation, these types of things. Confidence in the technology, basically. Any other questions or comments? So before some people logged on, we were talking about quantum support vector machines. Zoran, who works at Amgen, it was a big paper. It still is at that time on IEEE for explainable AI. He said binary classification of rheumatoid arthritis, if they'd have to stay on medicine or not. So I definitely enjoyed reading that a couple times. Anybody we haven't heard from? So Carlos, Edwin,
maybe just to maybe ask you one more question, like you're talking about, I've been familiarizing of late with annealing versus the gate-based kind of computers. Which ones are you seeing making more progress on in health,
Yeah,
or what
so
are the challenges?
yeah, so for real hardware, probably what's winning right now is ion trap. So you have IonQ, you have Quantinuum. You know, for gate-based superconducting qubits, definitely IBM, Qiskit, Rigetti, and then silicon spin is Intel. And they had news today. And then neutral atom, so atom computing, they're in the mix. So PsiQuantum and Xanadu for photonics. So, you know, they could break, right? And we haven't heard from a number of these. We haven't really heard from Xanadu a lot since they claimed quantum supremacy in June 2022. So that's photonics, quantum computing. And it's hard to tell, right? But IBM just had their big news. They actually kind of said 100,000 qubits by 2033. So, you know, that's not as much as what people were expecting. I think a lot of people were expecting 1 million by the end of this decade. But if you want to research it and read a lot of papers, I would suggest the IonQ and Quantinuum papers in literature. Quantinuum just says 32 qubits GHZ entanglement, which is I think it's multi-qubit entanglement, so it's more than just a CNOT gate over 32 qubits. So that's encouraging. But as far as just throwing a lot of data at it and at processing in hybrid environments with quantum, it may be some time, right? Most of these are proof of concept still, like really small data sets, not something like you know, thousands of pictures kind of thing. Yeah, so those are the ones that I would check. D-Wave, you know, we mentioned D-Wave quantum annealing for sure. That one too.
Yeah, I wish you'd put some of that in the chat, because I'm not able to like make out the spellings of some of the.
Yeah. So which technology?
I think you talked of IonQ or something.
Yeah.
Adam something.
Yeah,
Yeah.
so IonQ and Quantinuum are ion trap. And then those are those two. And I would especially keep an eye on those for sure, because IonQ said they're making a manufacturing facility first half of next year. And then so you have Google, IBM, Rigetti, and others and that's more like gate-based. And this is theoretically the most powerful one. It has some issues with noise and, you know, faults, errors, those types of things. So it's typically referred to as gate-based superconducting qubits. And then, so you have, you know, so Intel and others are, you know, this silicon spin, which is promising because with silicon spin, you can use existing lines, like how you would make phones today classically. So that's that one. And then so atom computing is neutral atom. And then you have the last two, PsiQuantum and Xanadu are photonics, which in theory should be room temperature. So they have trade-offs, but time will tell. I don't think all of these will make it. Like for just mainstream applications, most experts say maybe 2 or 3 will kind of pan out. And it's a mixture because IBM and Google and Rigetti, they require liquid helium at like millikelvin temperatures. But if it works, if they can get it to work, then they would have the best quantum computer on paper. The ion trap stuff is kind of working today. You know, their qubits aren't high, like 25. And I think even in the next, what was it, 2016, something like that, they might only be like 100 or I think it's more like 1,000. So you have to plan that because, you know, don't think millions of qubits with any of these. And I would say, especially in the next 2 or 3 years, although they have the potential to. So
So there's another player in the neutral atom market, or a wannabe player. They are advertising a dual mode quantum computer using neutral atoms and analog computers. So there could be some interesting crossover there. People have long abandoned analog computers because everybody thinks digital is so much better, but there are things analog computers do effortlessly, like real-time integration and stuff like that. But
Yeah,
those
I don't,
guys, they let it slip that they don't quite have their neutral atom up and running yet, but should be interesting. It's another player, so
yeah,
I'm
vacuum tubes were considered analog, correct?
uh they're analog, but they were operated in digital mode. I mean, you can the first computers were built with these tiny little things called nuvistors, which were just basically tiny little vacuum tubes that were stuffed in little aluminum cans about the size of between a pencil eraser and a thimble. And so they can be built to operate as electrical switches, like on and off. You operate them in a digital mode. They work essentially exactly the same way as a transistor does. It's an analog device, but we use them in a digital mode inside of all of our computers.
Yeah, I mean, some of these could get lucky because there's things out there. So most of the circuits we've been talking about with, gates are state vector circuits, and that you can do any type of, entanglement, but they're limited in qubits. So there's this thing out here called tensor network quantum circuits, and NVIDIA talks about these because that's where they got over 1,000 qubits simulated with like 800 GPUs, right? Like this impractical kind of thing, proof of concept. And then if that fits in a specific architecture where you don't need that much entanglement, then that might be a tensor network quantum circuit application there. Now, thinking to the future, and actually, if you did not know, Penny Lane has a default .qtrit simulator. So this is not qubits, this is qtrits, and the output is not 0, 1, it's 0, 1, and 2. And then I got on it, and then I figured out a way to get a 0, 1, or 2 output based on the entangling gates, and partly studying the model to get whatever output I want. So this could open up for additional processing power, simulated, or if there's like a quantum computer that could run it. And you could do a Q cord, which is 4, so that'd be 0, 1, 2, 3. And the formula to get better or more information is on a qtrit, it's 3 to the n. On a Q cord, it's 4 to the n. So instead of the qubit being 2 to the n. There could be a breakthrough there, but it's hard to work with qtrits in binary code because the output is not 0 or 1, it's 0, 1, 2. But a Q cord might be easier because it's 0, 1, 2, 3. And then plus you have that, theoretically higher amount of feature space that's and especially amount of information that you could deal with a Q cord is higher than the other two. But there is a real qtrit simulator out there. It's free. So I would definitely hop on, do that demo. It's on Penny Lane's demos for sure. And data re-uploading. Is anybody familiar with this term? So I think in classical, it's just called data uploading. And then when you're using a qubit with it, you only need a single qubit in order to perform a classification 0 or 1. So I had some success with that, adding a single gate to it, a little bit slower, but better numbers for 10 epochs there. So yes, there's all this cool stuff, and it'll narrow down, right? Like so, or the B8, beta whatever versus VHS. VHS 1, right? And I think Betamax was actually a little bit better technology. So it's a number of it's money, it's innovation. A lot of this is, they started off as government projects. I think at least Transmon or gate-based superconducting qubits, they weren't in industry, they've moved to industry. And industry has maybe a more diverse set of skills or resources to deal with. for innovation, you know, for improving the tech beyond what the government did. So yeah, so it's definitely a fun and exciting field. And coming back to programming, you know, definitely check out the demos for a lot of these things. So the demos, Qiskit has a bunch for quantum machine learning. PennyLane has a bunch, and I would check out especially the PennyLane, the other ones, the Qtrits and data re-uploading, those types of things. Kind of fun, and then you can modify them, make them better. Usually they're not perfected like some of the Google TensorFlow quantum is just like, we got 100%. And I'm like, okay, what am I going to do with this? So PyTorch, if you're advanced, actually it's Torch Quantum. It's by MIT. It's the PyTorch quantum equivalent. They have one I'm trying to get to work. And it's basically, instead of training the quantum circuit, the parameters, it's training to get the optimal quantum circuit. So it had a bunch of installs, and I can't get this thing to work, but you know, there's a lot of stuff out there, I would say, to learn and then develop. Hopefully get off on your own with that too. Awesome. Any go ahead, Edwin.
Would you mind clarifying a bit about adiabatic?
Adiabatic. Oh, did somebody mention this? It was that typically associated with quantum annealing, adiabatic. I think that's usually used, but adiabatic I think comes from non-heat is technically what it means, but you know, not quite sure of the foundation of the word.
Okay.
And yeah, so Carlos put it in the chat there too. So feel free to come on, Carlos, if you have anything. Torch Quantum, the MIT Hand Lab. Like I said, I'm kind of struggling with them. I got some of the simpler ones to work, but this is just some programming 101 I have to figure out with the installs, you know, basically. But one of them, the optimizing the quantum circuit one, that one has maybe like, you know, at least 10 or 12, you know, it's slow. It has some pretty significant installs up front. And they've presented it at a couple different, actually, sometimes the gentleman that puts these up, he comes to the discussion. They presented it, I think, at 2 different conferences. And I've seen about 4 papers I've come across use Torch Quantum. So, you know, it's likely there's going to be many, right? Like just so you have PyTorch and TensorFlow, now you have Torch Quantum and TensorFlow Quantum. Yeah, so like I said, it's hard to predict everything that's going to happen. You just see some good stuff happening now. I would say on the hardware side, the ion trap. On the similar side, the GPU simulators, multi-GPU simulators, and I think you have to the cuQuantum, the NVIDIA software is and I'll just type that in there. NVIDIA cuQuantum. The software is free, but the GPUs are not. I think that's typically how that one works. But so PennyLane, I'll just type in some simulators here. You have default.qubit, which pretty much works on anything. The lightning.qubit, I've had issues with, like only simple things I can get. And then you also have lightning.gpu. So if you ever get to that point, you know, you're programming every day, you could try all these out. So your installs goes up, and like I said, you have to figure out a way to figure out the cuQuantum GPU accessing it, because it's not user friendly to me. I've tried, right? So the lightning and there's lightning.cocos too. That's their new one as of like this past month or 2. So lightning.cocos gets you into CPU and GPU environments. And I would read that page for Cocos, because it says we're going to start to see a lot more awesome stuff, you know, especially on the side of GPU accelerated simulators. I didn't get to read that whole thing, but I would check out Cocos. So it's one of those things I still haven't gotten to run, but there's a million things to do. Any other last questions or comments? Appreciate everybody coming on. And yeah, thanks everybody. And so, just start your quantum journey if you haven't. And I would always make a preference to running experiments on Google Colab, locally on a Jupyter Lab notebook, Qiskit. You can do Qiskit for free. Colab, you typically have to pay, especially for GPUs. Jupyter Lab notebooks, those are, everywhere. So Kaggle, you can have one on your desktop, basically. So, definitely, just get out there and run and supplement it with, instructional lectures, and then definitely papers too, literature. But at the end of the game, you really want to have something to show. So just run a bunch of demos. If you can't afford it, find the free ones. You could run all of them for free on Qiskit, just without a GPU accelerated. So I would definitely start there, kind of get your feet wet. So awesome. Any other last questions or comments?
Best places to start for learning materials?
You said for Qiskit?
Yeah, any.
Yeah, it's just
Any you'd recommend.
Qiskit.org. And then the key thing with that is you want to get to the point where you have a user ID, or it's like a token ID, but you don't really need to use that on Qiskit. That's only if you go to use it on your local, Jupyter Lab notebook. And then I'll get you a good link. So Qiskit.org, and there's a good site. So they're basically quantum circuits, and you push one button and it sends it straight to IBM Composer. So this is entanglement Qiskit, and it helps just to run. So you could run right away on like a 7-qubit. Oh, here it is. So I would check that out. That last link in there. Because you could run a bunch of circuits. It's just 2 clicks. Click to run, and then click again or click to open in IBM Quantum Composer, that black box. Click again to run on a quantum computer once you get set up. Awesome. Well, I appreciate everybody coming on. This is discussion 87, June 15th, 2023. And good luck in your quantum journey. I hope to see you next time. Take care.
Thank you, Kevin. Thank you so much.
Thank you.
Yeah.